right and left. So for example, U1, so this was empty here, and this was the entire U1, right? And where did we map U1? We just project on the x-axis. So this guy projects like that, this guy projects like that. So this is our map phi 1, and this is phi 1 inverse. So phi 1 mapping U1 to R, the circle, is a one-dimensional manifold, right? Because you need just a one coordinate to represent a point on the circle. So I'm mapping to R1 because it's one-dimensional manifold. Phi was defined by what? Phi 1 takes a point on the circle, so it's y, and we're projecting on the x-axis. Okay. The projection is always easy. The a little bit more challenging part is to define the inverse, which is from R, give me a point on the circle. Right? So phi 1 of x, please give me a point on the circle, which is some x and y. Well, x is the same, and y is square root 1 minus x squared. Right? And if you go to the lecture, we showed that if you differentiate this guy, that's okay, because when you differentiate it, you have this guy in the denominator. It's well defined if x is not 1, and we're excluding this point already in our U1. So that's okay. Then we defined U2, which is in the lower thing. Then we define U3. So let's have U3 here. If you remember, this is U3. This is U3. So we project on the y-axis. So this is the y copy of R, another copy of R. So this was our phi 3, this was our phi 3 inverse. So phi 3 maps U3 to R, another copy of R, by phi 3 of x and y. We're projecting now on the y, phi 3 inverse from R to U3. Phi 3 inverse of y is what? What was that?
Square root of 1 minus y square and just y.
Very good. So now the overlap is here. Right? So U1 intersection of U3 is non-empty. It's actually equal to every x and y in S1 such that x greater than 0, y greater than 0, and this is the first quadrant. It's non-empty, obviously. So we need to have the composite map. You can see it from here. So this is the x copy of R, this is the y copy. I need to go from x to y smoothly and going back smoothly. I need to show that the composite map is well defined. So I need to show that phi 1 inverse, and I'll compose it with phi 3 is a diffeomorphism, right? And let's see how we do that, please. So phi 1 inverse takes what? This is phi 1 inverse. So phi 1 inverse takes a point x. So let's see. So this is phi 3 of. Phi 1 inverse takes x and gives you 2 points, x and 1 minus x squared, right? And please let's apply phi 3 to that. Phi 3 applying to a point. Here is phi 3 applying to a point. I take the second coordinate. So this is square root minus x squared. Any question that this is the composite map? Okay. So it's as if this is actually y as a function of x. And we need to prove that it's a diffeomorphism. First of all, it's well defined. There's nothing wrong about this. And if you do the derivative, it's negative x over this guy. So it has a problem only when x equals 1 or negative 1, and this point is not there in the set, right? So this is actually smooth enough. You can differentiate it infinite number of times.
Can you read the last line, please?
This one or that one?
That one.
This one.
Yeah, how did we get this?
You apply phi 1 inverse first. You see phi 1 inverse, the red, the underlined red?
Okay.
You take x and give me 2 things. So here are the 2 things. And then you apply phi 3 to the result. This is the interpretation of the composition. You apply this guy and then you apply that guy. Apply phi 3 to the result. Here's phi 3, which I circled. Phi 3 takes 2 things and gives you the second. So it takes 2 things and gives you the second. So this is the composite map, phi3 composite of phi1 inverse. It takes x and gives you square root 1 minus x squared. Okay? It's a map from R to R, different copy of R, and we need on this set, only on this set, right? So yeah, you can see that, yeah, it's very well defined on this set, and the derivative is continuous, and you can differentiate infinite number of times because x equal 1 is not in that set, right? Any question about that? So to complete the proof, you need to show compatibility between all the things. I will not do it, of course, here, okay? Because we have overlap, too many overlaps. This is only one overlap. We will have another overlap here, another overlap there, and there, okay? And as you can see, it's tedious if you have too many overlaps, so it will always be smart if you come up with little and little coordinates, fewer coordinate charts to represent your manifold, okay? So for this, let's take the example of the sphere. So I have proved S2 sphere is a manifold. So I have the sphere. So how can I deal with the sphere? Well, I can do the same way, the same analogy we did with the circle. In a circle, we can have the upper hemisphere, and we'll exclude the equator, the lower hemisphere, then we have the right and the left. And now, did we cover it or not yet? Because there's still 2 points, right? So I have to take the fore and aft. So this is like 6 maps and too many intersections. So let's do a little bit more small. We will define the following. I'll do it with you using, which is the standard actually, stereographic projection. So in the stereographic projection, you choose a point. Any point, pick any point you like in the sphere, maybe this one, which is the North Pole. I'll pick this one. And you pick a plane, say, I will pick this plane, the XY plane. So stereographic projection from, you can do it from any point, I will do it from the North Pole. Okay? So, like I said, you can have the upper hemisphere and just project on the XY plane. But this will cover what? This will cover the upper hemisphere only. So, this is a different projection. And luckily, it covers the entire thing except B. So, actually, our U1 will be the entire S2 except the B. So, just need one more map or one more chart to cover B, and that's it. Okay? So let's see how we do that. What do you mean you cover this guy? I mean, I will provide you with a diffeomorphism that takes any point in U1, which means any point in the sphere except the North Pole, and give you what? Should I give you what? I map it to where?
R3.
R, yeah, this was R what?
R2.
R2, right? Sphere is two-dimensional manifold because you need 2 coordinates to tell me what's your point on the sphere. So I need to map to R2. Very good. So, okay, let's see how this map works. So give me any point on the sphere, any point except the North Pole, like this point, for example, P. So it has, if this is the X, for example, and this is the Z coordinate of it, right? You just draw a line, connect a line from your point that you choose to the point that you want to project onto that plane. So this gives you the X coordinate of the projection. Okay? This entire thing is the X coordinate of the projection. And you can do the same for Y. So phi1 will take X, Y, Z and project it into the XY plane, but it's not just little x and y, it's these x's and y's. How to get them? That's super easy. So tan of this angle is what? Remember, this is 1, right? So it's 1 divided by x. So 1 divided by x is equal to, from this small, thing, it's little z divided by x minus x. So you can solve for large x in terms of x and z. Okay? And obviously, if you do the same for y, you will get similar results. So this is y over 1 minus. So this guy should be here. Actually, I prefer to do like this. So this is x 1 minus z, y 1 minus z. Any question about that? Is the map well defined? When it has a problem with z equal 1, this is why precisely we excluded this guy. Right? So nothing wrong. You want to differentiate, differentiate. Here's the Jacobian. So differentiate this guy with respect to x, y, and z. Here's with respect to x, easy, y 0. Z is what? 1 minus z all squared. And y similarly. So this is 0, 1 minus z, and y 1 minus z all squared. They are all continuous and smooth actually. They have a problem with z equal 1, but we exclude this one, so we'll find. Okay? Projection is not hard. Projection is always easy. The issue is you need to do the inverse. If I give you large x and large y now, you need to provide me x, y, and z back, right? This was always the harder step. So you need to provide me with phi 1 inverse, which will map the R2 to U1. So phi 1 inverse will take large x, large y, and should give me 3 coordinates, a point on the sphere, in terms of large x, large y only, right? We'll do it from geometry, it's nothing hard, but let's see. If you have large x, I can give you little x easily if I know z, right? And the same for y. So how to get z in terms of large x and large y? This will complete everything. So you can get it from this identity. So let's do x squared, large y squared plus 1. What is that? This is x 1 minus z all squared, y 1 minus z all squared plus 1. So this is x squared, y squared plus 1 minus z all squared, which is z squared 1 minus 2z over 1 minus z all squared. And you can now observe these guys are 1. On the sphere, 1 plus 1 is another 1. So I have 2, 1 minus z over 1 minus z squared. So that's interesting to be 2 over 1 minus z. So I can solve for z in terms of large x and large y. I will call this guy as, because I will repeat it so many times, I'll call it delta. So this actually will give you the coordinates here, fine. So this is 2x over delta, 2y over delta. Sorry. This is 2, I guess large x, no. Let's see, I'm getting x. So yeah, 2 large x, 2 large y over delta. And here x squared, y squared minus 1 over delta. You can check it. This is obvious. You just need one more step to get this guy. So I provided you with phi inverse. Please check that it's, first of all, it's very well defined because this is never 0 on the sphere, right? Do your derivatives and you'll find everything is okay. Am I done with proof that S2 is a manifold? What's missing here?
We can just pick one other point and
Very good. Take any point like the South Pole, for example, and do the stereographic projection, then we'll cover B. Or just pick the upper hemisphere and do the x little xy projection. This will also cover the little b, right? This will be in the homework or something. Any questions? Okay, so we'll have more examples for manifolds. Like any collection of rank K, smooth functions on Rn, they form a manifold for n minus k dimensional manifold. So you have collection of functions f1 up to fm. Every one of them, they take a point in Rn and gives you just a real number. Okay. these guys, if they are rank k, so if they are full rank, m will equal k. So m in general is greater than or equal to. If they are full rank, then you will have k functions, rank k. Each one just maps Rn into R, gives you a value. So these guys, they will define an m minus k dimensional manifold in the following way. M will be every x in Rn such that if one of x is constant, say C1, if m of x is constant, say Cn. So this is a manifold. Let's see an example. So we have f1 is x plus y plus z. This is a function on R, f to another function of R, x squared plus y squared. Okay? So the level set where this is 1, some constant, maybe this is another constant, but for simplicity let's choose 1 for both of them. Okay? So this is a level set, this is a level set. The set containing these two level sets, the intersection of them, is a manifold. And we can prove that easily here. Let's visualize first. So like this is x, y, and z. This is a plane, right? This is a plane, this guy. And this guy is a cylinder, right? So the intersection between them, I have just a very little, here is it. Do you see it? So this is a plane, this is the cylinder.
It's problem.
What do you mean? It's not a parabola. It's not z equals x squared plus y.
Intersection between
I'm saying the manifold.
Oh, yeah, the manifold. Okay, yeah, that's right.
This is
Yeah. So this is the intersection of the plane and the cylinder, right? You see these kind of points. Actually, I should. So we can do the following. Maybe I can do what? I can do edit, copy figure actually, and can paste it here.
actually
There you